Hello everybody. So this is lecture number 9 in the series of fluid mechanics, and today we are going to discuss about surface tension. Okay, so our agenda is to discuss about surface tension. In the previous lecture we have discussed about Newtonian fluids, non-Newtonian fluids, right? So in this lecture we are going to discuss about surface tension. Okay, so why surface tension? Okay, so before starting about any topic or any subject, you should ask and the question first. Okay, then you will maybe you get more understanding or more clarity about the topic. Okay, clarity. Okay, so see why this surface tension came into picture. Okay, why we need to study this. Okay, so let's suppose a table is there. Okay, and when you pour water, means when you put a drop of water here. Okay, see, let's suppose this is a drop of water, right? Let's say water droplet. Okay, so now you see water droplet is there. So see, there is two fluid, right? One is the atmosphere, I mean we call it as the air. Okay, and another one is water droplet, right? So this I mean say this continuous line, that this white line, okay, this forms interface with the atmospheric gas, right? So everywhere there is atmospheric gas, and this region, that is inside of this white curve, there is water, right? And everywhere it's fluid. Okay, so this white line makes an interface, right, between the um, air and the water. For example, if you put this water in vacuum, what you will get is, when you put any water droplet in the vacuum, then see the water will not retains its shape. It will be like very in means it can't be in like a drop form. Okay, it will just form a layer of things, or it will just get drop out of this table. Okay, it will not form this spherical kind of shape. It's actually not a spherical, perfect spherical shape, but it's a kind of a spherical shape, right? And when you will do this experiment in vacuum, you will not encounter this kind of things. So I mean, there is something that because of that, this water droplet is not expanding freely. I mean, here you will see that the water droplet is expanding and get expanding till infinite time, right? It will get, I mean, it's expanding. There is nothing which can resist this water droplet to expand, I mean to burst out, right? So atmospheric air, it prevents this water droplet from infinite expanding, right? It will not get just burst out just by keeping it on a table, a drop of water, right? So see why. Okay, so now you understand, right? When two types of fluids are there, there is some interface will be there, right? It should be there, there is no doubt about it. Okay, so see, one distinction you can make at the interface. For example, let's suppose a water droplet is there, okay, at the interface. Okay, that green one. Okay, and now if we, and the other water droplets are this brown one. Okay, so what's the difference between this brown one and the green one is that see, this brown one having, I means they are present in inside of the water droplet. So this green one is also present inside of the water droplet, but the difference is that this, if you see this I mean this what to say, brown droplets, I mean brown liquid particles. So we will call it as internal molecules. Okay, internal molecules of water. Okay, so if you see this water molecules will face, I mean they are going to repel each other with equal and equal forces because of their close packing, right? So I mean they are closely packed from outside. Okay, for example, if you see this one, everywhere there is a brown fluid, right? Brown molecules. So it will what to say, it will faces or experiences forces from all direction, right? From all direction. But when you see these green molecules, okay, these are only packed from one side, okay, from one side. So why I am saying, see this the green butter molecules, there is there is only neighbor liquid particles on one side, right? If you see this if you will get a shade of air, the left side is your atmospheric and the right side you will experience some fluid particles, okay. So only one side you will getting experience of liquid particles, okay, and from one side you will not encounter any fluid particles, okay. So that's why there is a non-uniformity in the force will occur. Non-uniformity in forces, non-uniform force actually in force, okay. So force will only act from one direction, right? Right, we can see it here, right? Force can only act from one direction, okay, and another side there is no force acting, right? So it's half of the neighbors are missing, so the mechanical effect that surface is facing is known as surface tension, okay. So there is only half of the neighbor is present, so mechanism that occur, that means mechanical effect will get there. Suppose that here the particle that is deep inside, these are having experiences of forces from all direction, but the particle which are at the interface, they will not experience forces from all direction, okay. So there must be some mechanical effect, right? And the particles are not in the equilibrium, that means there are something which are acting. So that's technical term, in terms of technical term, it is known as, to counter this we can just think like that, there is one mechanical effect which is known as surface tension, okay. Okay, so now we have understood surface tension in very general ways. You can explain this to any child or any person which having no knowledge about fluid and all the things, okay. So this is all about surface tension, means how we like, how the first person think about the surface tension, okay, how the concept get developed here. So the concept developed from here only, from these conditions only. Now we will see some technical terms of the surface tension. So for example, any surface is there, like we have seen it, right? Some table is there, some fluid particle have been there, okay. So there is an interface, right? These interfaces, this neighbor particles, air is there and the water is there, so this interface will be there, okay. So if you cut a length dl is made at an interfacial surface. If you cut any any length dl, okay, so let's put this dl, okay, at the interface only, not exactly this, from here to here, okay. So this length, okay, this length, let's suppose call it dl, and it should be cut at the interface only, okay, not any internal parts or any external parts of the atmosphere or the liquid, okay. Okay, so when you cut this, an equal and opposite forces of magnitude gamma dl are exposed normal to the cut and parallel to the surface, okay, where gamma is the coefficient of surface tension. When you put this length, some normal forces will act from both the direction and parallel to the surface as well, and that force is equal to gamma into dl, okay. So dl will be the length of this interface, okay, and gamma is known as coefficient of surface tension, okay. coefficient of surface tension. Okay, so this is known as coefficient of surface tension. Okay, and the as you see this the unit of the multiplying both of them, you will get some forces, right? I told you some normal forces will act here, I mean in normal direction. No need to write in here. Okay, in the normal direction of the surface, so there must be some kind of force. Okay, so the unit of gamma, I mean this coefficient of surface tension is force per unit length. Okay, so this is the unit. I mean Newton per meter, right? This will the SI unit of this gamma, right? Okay, and this one the one concept that we can think it of in term of force, but the another concept is that uh, when you cut area dA, let's suppose if you take area here, I mean 2D object. Okay, 2D object dA area. Okay, you have cut it like this. Okay, and elemental area will be there, that is dA. So this requires burst to be done of amount gamma into dA. Okay, so I mean if you want to calculate the energy that it's need to be done to, I mean resist this, I mean for example if you take this drop of water, if you cut any section of the fluid and you are getting some you are cut it such that the area which it is covering is dA. So let's suppose to for the fluid to having in this kind of shape, they are having some work need to be done, right? Otherwise it can get just burst up, and it will like in the case of vacuum we have seen that it will can just pure it out from anywhere. Okay, so this is not case, this is not in case of this example. So some work has to be done, and that work is done is equal to gamma into d. Okay, this is the second concept that we can think it of gamma as, and the term which is coined by this gamma into d is known as surface energy, kind of surface, I mean energy. Okay, so this is known as surface energy. Okay, so gamma into d is your surface energy. So from here you can tell that gamma is, I mean it's known as same as coefficient of surface tension. So here the unit is coming as energy per unit area, right? Energy per unit area. So if you do the dimension analysis, you will get force into length, and area is length by length. Okay, so the fundamental unit will remain same, force per unit length. Okay, so there is dimension similarity here. Okay, so I mean dimension informativity, so you no need to worry about that. So there is two way we can think it of as a coefficient of friction. The first one is like in terms of forces and length, and the second one in terms of surface energy and I mean surface area. Okay, okay, so I mean let's see, I will write some values, so just remember it. You will find it useful when you're trying to solve program when it's not given. Usually it would be given here anywhere. So gamma is equal to 0.073. Just I'm giving it a idea. Okay, so what should be the values of gamma or anything? The gamma would be the coefficient of surface friction, coefficient of surface tension would be 0.073. It is for air water interface. Okay, air water interface. Okay, and okay, that is enough for you to know. Okay, just I'm giving an idea of what's the order of value gamma holds. Okay, okay, so generally gamma decreases with liquid temperature and is zero at the critical point. Okay, okay, if the interface is curved, a mechanical balance so that there is a pressure difference across the interface, the pressure being higher on the concave side. Okay, so what I'm trying to say is, see, I will discuss some examples here. I mean just illustrate here and the idea of surface tension in a battery. Okay, just you have learn it here in a theory manner. Okay, how will be going to use in real world. Okay, so for example any cylinder was there. Okay, and we have cut it. Okay, we have cut it in half of I mean exactly equal to half of the cylinder. We cut it to make it equally half. Okay, and for example, okay, so this is the example number one. that we are going to discuss here. So what I try to I meant to say is, if a interface is curved, okay, this one is curved interface, right? Okay, and mechanical balance, so that there is a pressure difference across the interface. Okay, so I mean, for example, if you take the example of air and water interface, so there is some pressure difference, right? Water is having larger pressure, and air is having lower pressure. Okay, for to sustain in that drop format, the force should be equal, right? Force applied from the air and the force applied from water should be equal. That's why they are I mean, they are able to sustain that shape. Okay, they are able to sustain in that shape. Okay, so I mean, there is some pressure difference would be there at the interface. So for, I mean, the pressure being higher on the concave side, right? So this is the concave side, so pressure would be higher here. So that means the forces is acting in the like this direction, right? And some atmospheric air will also act, right? So it will act in this direction, right? So I mean, there is two interfaces, one is in that side and another one is in this side. Okay, so the length, let's suppose we call it L. Here as well the same length would be there. Okay, and the force it act, no, I mean, the pressure difference is delta P, so we can write this in term of force as a 2r into L, right? 2r is this distance and L is this distance. So if we multiply force with the help of area, we will get the forces here. Okay, so if we just take it in equilibrium of both the forces, we will get see, this one is length L. Okay, so we know that gamma L would be the I mean, surface tension, I mean, surface forces from this direction and this direction as well. So we will add both of them, gamma L plus gamma L, and it would be equal to 2r L plus delta P. Okay, so now we will calculate delta P. I mean, the pressure difference is 2 gamma L divided by 2r L. Okay, so just is equal to gamma by r. Okay, so this would be the case in the cylinder. Okay, so just remember that this could be very useful if you are going to solve, I mean, objective questions and altogether things. Okay, so now let's suppose we will discuss the second example for the case of a spherical, I mean, hemisphere. So some a sphere is there and we have cut it down in equally half portion. Okay, so again the same base, the area here is pi r square and the forces would be acting as delta P, right? And the whole this, I mean, this interface line is equal to 2, I mean, this radius is r. Okay, so it would be like 2 pi r into, I mean, this one is the length and gamma. Okay, so we know that surface area is length into gamma, that's why the length ever is, the interface length is equal to L. So now we will equate both of them and we will get pi r square into delta P is equal to 2 pi r into gamma, right? So pi cancel, r cancel on both sides, so we will get a pressure difference is equal to gamma upon r. Okay, sorry, 2 gamma upon r. Okay, so this would be the pressure difference in case of a sphere. Okay, now we have seen two examples. Now we will going to discuss about some, I mean, a general equation that we can made it for any curved surface, and it would be like, so let's suppose not here, okay, so let's suppose some r1 radius is here and some r2 radius is here. Okay, and some forces is acting, I mean, this delta P into dA, the elemental area, we are taking this curved surface as a elemental area. Okay, and some that surface force is acting, that is, let's suppose gamma L2, in this direction gamma L3, in this direction it is gamma del I mean, gamma dL2, and this one is 1. Okay, we are taking a rectangular surface like kind of thing. Okay, that's why L1 here and L2 here. For elemental length we will write as dL2, dL1 and dL1. Okay, just for the sake of elemental, I mean, very small body, these are defined for very elemental objects. Okay, we can't define it for a very large object or kind of something. Okay, okay, so we can use this result to predict the pressure inside a soap bubble. Okay. Okay, so we will discuss that. So we have taken a general case of an arbitrary curved interface whose principal radii of curvature are r1 and r2. A force balance normal to the surface will show that the pressure increase on the concave side. So how much pressure is going to develop? So a general formula is there, that is delta P equal to gamma okay, R1 okay plus R2 okay. So or we can write it as delta P is gamma 1 by R1 plus 1 by R2 okay. So we can directly find these values for these cases from this general expression. For this case, see, one R1 is, R1 is, this one is R and another R is infinity. So we can write is R1 R plus 1 by infinity. For cylinder case, we will get gamma by R. Alright, this we have get here. So we can confirm it is the correct formula here as well. We are having the same R here and the same R here. So we can write it as 1 by R plus 1 by R into gamma is equal to 2 gamma by R. Okay. Sorry, 2 gamma by R. So we can confirm these formulas for a spherical body as well. Okay. Now, so we can use this result to predict the pressure inside a soap bubble which has two interfaces with air and inner and outer surface of nearly the same radius. Okay. So what I'm going to try to say is a soap bubble is there. So a bubble is there, air is there inside the bubble as well and outside as well. Okay. So first we will write the formula for the one interface. So let's suppose the first interface is inner one. For inner one we can write it as we have seen the formula for spherical, right? 2 gamma R, and we will write the P2 pressure difference for the outer air. Okay, we will write it as a 2. So it will again got 2 gamma by R. We have seen there, right? So the overall this will become P bubble. So total pressure that bubble is going to develop is 2 gamma R plus 2 gamma R, right? So it will become 4 gamma R. Now if you see in the case of any just butter droplet, there is only one interface, right? And let's suppose we are taking it as a spherical shape. So the delta P that droplets will face is just gamma by R, 2 gamma by R, right? So there is no two interfaces, only one interface there. So 2 gamma R, we are taking it as a ideal spherical objects. Okay, but in case of the soap bubble, I will write it as a soap bubble. Okay, bubble. So we'll get to 4 gamma by R. Okay. Now we have a study about surface tension. Okay, a second important surface effect is contact angle theta, okay, which appears when a liquid interface intersects with a solid interface. Okay, and the force balance would have then involved both gamma and theta. Okay, so we have to deal with the both gamma and theta. So for example, what I mean to say, this contact angle theta, we will discuss it here quickly. Contact angle theta. So say a table is there, a liquid is there, liquid droplet is there. Now if it is making angle theta and which is less than 90 degree, then we can say it a non-wetting liquid. Okay, and when theta is larger than 90 degree, we will simply call it as wet fluid. Okay, and this we will deal with both gamma and theta in case of dealing with the forces, force equilibrium or the force balance. Okay, so when theta is just greater than 90 degree, we will call it as wet liquid or the wet condition. Okay, that means liquid will wet the this what to say, this table or this is solid. Okay, so wet fluid. And when theta is less than 90 degree, okay, so we will call it non-wetting fluid. Okay? Non-wetting case of fluid or condition, anything. Okay, so this is important maybe it could be asked in objective question for 1 marks and 2 marks. Okay, and we will have to deal with both gamma and theta when we do the force balancing. Okay, so in this course we are not going to deal with this water droplet things. Okay, maybe we will discuss some exam a small programs or kind of something, but we are not going to discuss it explicitly here in this course. Okay, so my surface decision is done. So I hope you found this session interesting. So till then we will discuss surface tension, and in the next lectures we will discuss about vapor pressure and kind of thing. Okay, so till then keep running and goodbye.